Hello everyone. In this video we are going to introduce the notions of rational and irrational numbers as well as modular arithmetic. Alright, so first we're going to define the rational and irrational numbers. So all of these are real numbers, okay? And we say that a number q in the real numbers is rational if q can be written as a over b, with a and b both integers. And of course, we don't want to be dividing by 0, right? Because that's nonsense. And so we say that b is not equal to 0 as well. Okay? So these are basically just fractions. Integers are still fractions, right? So like 2 is 2 over 1, or 4 over 2, or negative 6 over negative 3, and so on, right? So these guys are still rational, but of course you get fractions that are not whole numbers as well, right? So like, 4/5, negative 27, 76. These guys are rational numbers, okay? And so it's very easy to define an irrational number. We simply say something is irrational if it's, again, a real number and it's not rational, right? So we don't need to have a real specific, definition with formulas or anything. It's simply if it can't be written in this fraction form with an integer over an integer, then it's irrational. So we should have some examples of these as well. So you're probably already familiar with some of them. So like e, pi, these are irrationals, the square root of 2. And in fact, any square root of a number that is not a perfect square. So square root of 3, square root of 4, of course, is rational because that's 2. But square root of 5, square root of 6, square root of 7, square root of 8, all of those are irrational up until square root of 9, right? And so anything that's not a perfect square inside, that will give you an irrational once you take the square root. So we will have more time to practice with these in general, but I wanted to show you just one proof using rationals just to kind of get the hang of what this might look like. So the statement here is that the sum of two rational numbers is still rational. Okay, so we've done similar things with like the sum of two odd numbers is even, or the sum of two even numbers is even, and so on. And so this should have a similar flavor, but of course we have a different definition to begin with, right? We're not using even or odd, we're using rational. So how do we prove this? Well, we should start with two rational numbers, right? So I'm going to let q and r be rational. So now what does this mean? Well, by definition, this means that q can be written as a over b, and r can be written as, again, maybe not the same a over b, so I'm going to say c over d, where all of these are integers, right? So they're all in z, and b and d are not equal to 0, right? Because we're dividing by them. Okay, so that is just from the definition. And then we want to look at their sum. Okay, so given this, hence q plus r is a over b plus c over d. Well, how do we add fractions, right? If I see like 1/3 plus 1/2, I'm going to want to get that in terms of 6, right? I want a common denominator. And so here, I'm going to, multiply this guy by d over d, this guy by b over b to get the common denominator of bd. And so I get AD plus BC all over BD. All right. Well, this is great, right? Because I have a number over a number, and we know that the integers are closed under multiplication and addition. So I'll just say where AD plus BC and BD are integers. Since B, now what's the other thing we need, right? So we have integer over integer, but we also need our denominator to not be 0 like we had before. And so since B and D are not equal to 0, their product is also not equal to 0. So q plus r is rational, right? It fits the definition. It is an integer over an integer, and its denominator is non-zero. So now for your first exercise, I want to know what your favorite rational number is. I assume that's going to say a lot about you as a person. And second, I want you to prove that the product of two rationals is rational, and I would, look closely at how do we do the sum. And this should actually be a little bit easier because you're not going to need to worry about a common denominator when you're multiplying like you did when you were adding. And really try to get like complete sentences here and work on, definitions, and I can give you feedback on how that looks, right, as you're starting to think toward homework or tests and how proof should be written. So the next topic, so we'll work on some proofs later, not in this video, but I just want to try to start to get a grasp of what modular arithmetic is. So I'm going to do that through an example. So what happens when you divide 83 by 6? So if you just do, the division you were probably taught way back, right? It goes into 8 once, minus 6 is 2, we get 23, 6 goes in 3 times, minus 18, and we have a remainder of 5, right? And in general, what is always going to be true of our remainders? Whenever we talk about a remainder and how much is left over, it's always less than the number we divide by, right? Because otherwise, if it were greater, we would just have that go in one more time and get a smaller remainder, right? So this is all kind of examples toward the division algorithm. We're not going to prove this. You don't really need to memorize this, but I just want you to have seen it because this is where modular arithmetic is really coming from. So here's the statement. It says, let a and b be integers with b greater than 0. Then there exists some other integers, q and r, such that this is true. So, this might look like nonsense. What does this really mean? So b is the thing you divide by. This is basically just saying divide a by b. Q is the quotient. That's why we write q. It's how many times it goes in. And r is the remainder. Okay? So then basically this says b goes into a q times. And then has remainder r. And then the second thing that we have, this other condition here in red, is just saying what I was saying earlier, right? That your remainder is always less than the thing you're dividing by. So let's try to do a few examples to get the hang of this, okay? So this first one, we've already kind of done, but just not in this form. So right, our A was 83, our B was 6, and it says that this goes in 13 times and has remainder 5, okay? So then what about something like 14 divided by 2? Well, 14 is 2 times 7 plus 0, right? And so in this case, our remainder is 0 because 2 evenly goes into 14. And that's allowed to be a remainder. Now what about negative 29 divided by 3? So like negative 29 over 3. Well, you could say that 3 goes in, right, like negative 9 times, if you will. But why is that going to be a problem? So let's look at that real fast. So 3 times negative 9, but then it'd be minus 2, right, because that's negative 27. But I want something that's non-negative here. So this is bad. This needs to be greater than or equal to 0. And so the way I actually want to view this is add 3 there. So it's really 3 times negative 10. I go down to negative 30, and then I add 1 up. Okay? So negative numbers can be a little bit weird because of that, but these are some examples. So I keep writing this thing modular arithmetic. What does it mean? Well, you already have all of your knowledge. So in the case where we're dividing A by B, right, so like we've been doing before, then we use the symbol mod. We say A mod B is equal to R to mean this is the same thing as A is equal to B cubed plus R. So basically, we say A mod B is R if R is the remainder when you divide A by B, okay? So in all those examples, right, we had the remainder already figured out, and so it's just translating that into this notation. So we would say 83 mod 6 is equal to 5, right? This is the remainder, right? 14 mod 2, there is no remainder, right? Because 2 goes into 14 7 times evenly, so that would be 0. And then that last example, right, we had negative 29 mod 3. to get a positive remainder there, not a negative one, this actually had to be 1, right? Because we went in negative 10 to negative 30, and then we add 1. We had remainder 1 to get to negative 29. And so now for your second exercise, I just want you to practice some of this, okay? So again, think of this as your A, and this is your B, right? So you're dividing the thing on the left by the thing on the right. What are your remainders, right? So your answer should just be the remainders in all 4 of these cases. Thanks for watching.